How can energy loss be minimized through eddy current? How can energy loss be minimized through eddy current? So you have by using high resistance wire, by using insulated soft iron core, by using low resistance wire, by using tons of wires. So first of all, let's have a background of what eddy current is and how it's induced into how it's induced. So you have when electric motor moves, it experiences some sort of losses, you understand. So this loss could be like mechanical loss, it could be magnetic loss, it could be brush loss, and it could be copper loss, or what we call stray losses. So mechanical loss, magnetic loss, stray losses, brush loss, and all of that. So the magnetic loss is in two places. You have the hysteresis and eddy current. That's where you have the eddy current. And you have your eddy current when there is a change in intensity of magnetic fields. Are you getting it? So whether in the direction of the magnetic field or it's just a change in intensity, and you have an eddy current being induced, and this is going to be like a sort of current that swells around a conductor, you understand? So flowing like that in the magnetic field. So that's about that. So but now to answer these questions directly, how can energy loss be minimized through eddy current? Let's say you have a charge in a magnetic flux. So you have that across a square cross-sectional area. The power dissipated, are you getting it, in that cross-section is directly proportional to the square of that area, and you know, inversely proportional to what? To the distance, the length of the path, like that. So you have the power dissipated being directly proportional to the square of that area, that square cross-section, and the being inverse proportional to the length of the path. So if we have it like that, if power is P and you have that area to be H, you can have something like this. This is what you have as the power dissipated there. Now, if we want to reduce this power loss, are you getting it? The power being dissipated, what we'll do essentially would be to, if we increase the area, if we reduce the area, there will be a reduction in the power loss. So if we laminate that cross sections by an iron core, are you getting it? It's going to reduce the cross sectional area of that magnetic flux. So by virtue of that, the power would equally be what? Reduced. So if the cross section is laminated by an iron core, you understand, so such that the area reduces to half, reduces to half, reduces to half. This would reduce the power dissipated. Okay, and that's what we're talking about. So so if you divide that square into two rectangles by laminating the core, the power there would be cut into half. Are you getting it? And you have the distance reduced by what? By 3/4. All right, so if we do this, if this is laminated by an iron core, then the power loss will be reduced. So so let's link it to the options. By using high resistance wire, no. By using insulated soft iron core, yes, that is it. By using insulated soft iron core. So in essence, your answer is B, which is what? By using what? Insulated soft iron wires. By using insulated soft. C said by using low resistance wire, by using tons of wires. No. So remember, like I said, your eddy current is one of those two. We have hysteresis and we have the eddy current. The hysteresis is caused by magnetizations and demagnetizations of your field. Are you getting it? Why eddy current is induced by a change in intensity of magnetic flux. All right. So that's question number 29. Now moving on to question number 30 now. Question number 30 says, we're given a circuit. Says, from the diagram above, calculate the energy stored in the capacitor. Calculate the energy stored in the capacitor. Calculate the energy stored in the capacitor. So the circuit is, as we have seen, is you have something like this. You have something like that. We have 10 volts. And you have 8 microfarad. So from the diagram above, calculate this energy stored in the circuit. So here our capacitor is given to be 8 microfarad, which is 8 times 10 raised to the minus 6 farad, and your volt is given to be 10 volts. Now, so energy dissipated, E equals to half CV square, is equals to half CV square. Now from here, your energy dissipated will be equal to half. C is 8 times 10 raised to the power minus 6 times V is 10, so 10 squared. So you have E to be equals to, this divided by this, you have 4 times 10 raised to the power minus 6 times 100 times 10 raised to the power 2, and he would just be equal to 4 times 10 raised to the power minus 4. 4 times 10 raised to the power minus 4 joule. So that's question number 30. Now 31 says a constant force of 5 Newton. A constant force of 5 Newton acts for 5 seconds on a mass of 5 kg initially at rest. Calculate the final momentum. Calculate the final momentum. So we have a constant force of 5 Newton acting for 5 seconds, and he's acting upon a 5 kg initially at rest. Find the final momentum. So here, this is under momentum, as you can see. So we're giving force to be equals to, this is what we're giving. First to be equals to 5 Newton, and we're giving time t to be equals to 5 seconds. Now what you're going to apply here is your impulse is equals to momentum. Remember your Newton law of motions that says a body will remain in a state of rest of uniform motion in a straight line except is an externally applied force, except it's been acted upon by an externally applied force. Okay, so and you have your impulse to be reluctant to start moving or to stop moving when on motion. So your impulse is Ft. Your impulse is equal to force times time, expressed in Newton seconds, while your momentum is mass times velocity. Your impulse is mass times what? Velocity. So which is usually in kilogram meter per second. Kilogram meter per second. Okay, so now if we equate impulse to be equals to momentum, then we have 4 times time to be equals to the let me write it properly. You have your Ft equals to mv. But in this case now, there are two momentum. There is initial momentum and final momentum. You remember that the question says it's initially at rest. So we're going to have the momentum when it was resting and the final momentum when it finally took off. So here, because of that, we're not going to have Ft to be equals to mv minus mu, where mv here is the final momentum, while this is your initial momentum. Okay, all right, so now you can have that Ft to be equals to m to be equals to, sorry, you have your Ft to be equals to m into v minus u. Now we're giving u to be equals to what? Initially at rest. U is equals to 0 because it's what's initially at rest. That's initial velocity is 0. Okay, so now we would have our, let me move on to a blank screen. So force, which is 5 times 5 time, is equals to mass, that's 5, into final velocity we don't know, minus initial velocity, which is 0. So this is 25 equals to 5v. So v equals to 25 over 5. So your v equals to 5 meter per second. So your final momentum, which is equals to mv, is equals to 5 times 5, and this is equals to 25 kilogram meter per second. Okay,